Hey everyone, and thank you for joining the AstrumDrive podcast. Today we're joined by Nelson. He's the head of our physics department in AstrumDrive technology. So today we're going to review what we did in Sprint 4, and we're going to do short overview of the sprint planning we did for Sprint 5. So Nelson, if you don't mind, please go ahead and just give us a short overview. What did we achieve during Sprint 4? I know we did some really good job.
Hello, everyone. Thank you, Bailo. Sure. Yeah, we did some interesting approaches and a nice job this during the sprint. Let me summarize what we did during the sprint, the fourth sprint. So, but basically, we were reviewing a lot of articles that are doing different approaches to word drives. Some of them are doing the approaches to the Alcubierre word drives. And we study energy conditions. Basically, we want to know what happens with the energy conditions, but taking into account all that it is that comes from the warp drive, which means what happens when you find the Einstein's equations, the Einstein's field equations, and then see what happens with these equations, what these equations are telling us, and then going to the proper problems of the energy conditions, which have been studied a lot. But there are several things here that we wanted to find out before jumping into our proposal of the and it's different metric for the word drive. So basically, what we do is we took these articles. There's from Santos Pereira, it's a nice group from Brazil that they did some publications last year, and we were reproducing most of the the results they have. Well, we study what happens with the energy conditions that they have, and we obtain similar equations, not exactly the same. We got some differences, and this difference comes basically from what I just said, that is related to the fact that you have Einstein's equations, and once you have Einstein's equations, these equations, the whole system of equations tells you some, it gives you some information. This information is related to the fact that they all these equations are coupled and they have to be consistent. And in order to solve some of or to obtain some information from here, you manipulate equations, you do things, and you find the results. And what we found was just some constraints. These constraints are related to the fact that in the word drive, in the Alcubierre word drive, you generally can speak about a, a function that is like the shape of the bubble that is going to be the warp, and this function of the form of shape function is multiplied by velocity. In general, this velocity is dependent of time, and this function is dependent of the coordinates that lives on the hypersurface. uh, so you have this, and you all this stuff you can take it as just one function that is depending of time and the space. Basically, what we found is that if you take a look to the Einstein's equations, there are some constraints that you cannot avoid, and these constraints are related to the derivative of this function, this more general function, this product of the shape and the velocity, and it's very restrictive what you find. So basically, we found that there are some constraints here, and these constraints are interesting. We did it with a perfect fluid situation, which is the one that Santos Pereira has in their article. And of course, it's not that we obtain completely different results; it's that we obtain uh, results that are more uh, narrow in a sense. We think that most of the results don't take into account this. So far, part of the sprints we're working in now is exactly that. What's going on with this? What's going on with these conditions? And so basically, what we understood is that this perfect fluid situation tells you how it should be the relation between the pressure and the energy density. And Einstein's equations tells you, A, you have a specific relation, which is an equation state between these two things, these two parameters, that comes from the perfect fluid situation, and then also you have some constraints that comes from these functions that are which derivatives, some derivatives are zero, the functions, some other are just equal to each other, some second derivatives are zero, and if you put all those together, you find out that, for example, and this is like a spoiler alert for the next sprint, is you find that the weak energy conditions, which is well derived in every word, as far as I understand, that it should give you always a negative density energy. What this condition tells you is that no, it's not going to be negative because it's going to be zero all the time. And this is a new result. This is not necessarily the best and the great result that we're expecting, we're looking for a warp drive, but it's a different thing. It means that you have some constraints on the matter that you can put in these space times, and these constraints, when you take into account, it tells you, wait, the energy and the energy momentum tensor has to be this one, and apparently this is not completely clear at this point. This is something that we're doing now. So that's why the spoiler alert. Well, basically, also during the spring, we worked out the different things that we finished the Notarius paper. The problem with Notarius paper is what happens with a bit. We started with the horizon problem, which we understood just the first part, and now we're working more on this sprint. And also, we implemented all these energy momentum conservation things for a lot of several cases we know is okay in our mathematical notebook, which is, I told you, we always make some mathematical notebooks, and we found this is all working correctly. Basically, at the end, after checking this mathematical notebook, after checking all this, we found that apparently the only energy condition that is violated is the strong energy condition, and which is it follows a bit what Natarius results, which is the Natarius result is if you any generic warp drives in principle will violate either strong energy conditions or weak energy conditions. And Natarius paper, what he claims, he stated that of course if you assume that you are uh, fulfilling the strong energy conditions, it means that you have to violate the weak energy condition. He explained it there. But in that sense, the point is that if you don't violate the weak energy conditions, maybe you are violating the strong energy conditions, which is true. But then during the sprints, we're studying that maybe that's not really a big of a problem, and we will see that later during the next sprint. And basically we started with a, another group of articles from an author that published a very interesting paper last year, and his name is Eric Lenz, and we are studying one of his articles to start with. He proposed a very nice thing, which is basically you have the chief vector, and the chief vector follows some constraints, some assumptions that you have, which comes from the fact that you have Eulerian observers. These are free-falling observers that follow some geodesic equations. Basically, what he did was to think into a different type of chief vector that assumes a functional form that is dependent of the coordinates, and with that in mind, you obtain some field that gives you some constraints on the energy conditions, and under certain very specific ways of fulfilling these equations, you can have systems in principle, and he proved it in his article, where you obtain positive energy conditions solutions for instance, for the weak energy conditions, which is very nice. We're looking at this, and we studied. We back to the basics. We get back to the gravitation book of business book which is a very nice book, very old, but have all the information. It's very nice. I recommend it to read it. And we follow a lot of things there. We want us to understand from the very basis, and that's basically what we did during the sprint.
So, I mean, it's quite remarkable work, really, because we were able to uncover things which it seems that nobody saw before that, and we found some improvements of the existing work of some of the leading scientists in the field. And do you mind talking a little bit about the new spherical warp drive metric we uncovered? And I want you to go in a little bit of details how exactly we're going to examine the metric to understand is it useful.
Sure, yeah. Well, this is an way we were thinking of the different ways of writing a metric. There are some approaches that has been done by some people of working out Natarius metric or Lacouvire's metric and writing it in some pseudo spherical symmetry way. I mean, at the end of the day, these warps are spherical symmetric. The point is that once you start moving one direction, you have a preference in that direction. For instance, most of articles use C or X direction, and it means that you have some difference there. And then somehow, in a sense, you broke the spherical symmetric situation there. So we were thinking about what happens if you don't break from the very beginning. What happens? You don't break the spherical symmetric situation. You keep the symmetry and you find out what's going on, and then after you solve the problem, you break the symmetry, saying that you under this and this coordinates, specific coordinates, you move in that direction. So we construct the metric in that way, and we are looking into the Einstein's equations and doing more or less the same approach, the approach that Santos Pereira did, which is looking at the equations, looking at all Einstein's equations, trying to figure out the possible constraints that comes from there, and then first just in a very simple and dust situation, which is not a bit simpler than a perfect fluid energy momentum tensor, and then with an energy momentum tensor that is a perfect fluid, and look what's going on there basically. I can tell you that already we have some results. This is of course more complicated. For first, we are not longer using Cartesian coordinates, so you should expect some differences which we found in the equations, and it's not that easier to see which equations are giving you information, how to find the constraints. We found some things, but we're still on that. And the next steps is using these things and seeing if we can figure it out. What happens once you break exactly what will happen now is if we break this symmetry in some direction. You said we're moving in this direction. Oh, say what happens? What do you find? What happens with the shape function? What happens with the all these functions are appears in the word metric, and these are important. So basically, this is pretty much the approach we have so far. This is just the very beginning, of course. You can start putting more information here, and we will see. So just this is a starting point, and after you put more information, you complicate more the problem, and we're hoping to see what happens. But this is all in the view of we have been working in the previous work and seeing the work has been done and how these small differences could make maybe a big difference if you change, for instance, the metric that you're using, or even if it is easier for example to include different observers. This is all the observer dependent in the general relativity, so maybe what happens with different observers and in the spherical symmetric problem.
Awesome. Thank you very much for the overview. If you don't mind, let's go quickly over the sprint planning for the next sprint and just please give us some overview. What exactly do we plan to achieve into the current sprint?
Sure. Well, during the sprint, we're finishing working of the lens article, which is very important. Finding how he obtained his results and what are the drawbacks that are found there. There are some other in the same way that he found these articles, these results in his articles last year. There were another articles that these other articles were claiming that you have lots of problems, which and these are well important articles to review. And part of the work is exactly that, looking at what Lens did, checking what the problems are there. On the other hand, we're finishing what's the horizon problem, so we can look into the horizon problem in the spherical symmetric problem, and also starting checking what's happening with all the problems of causality and so on. On one hand, this on the other hand uh, is what we're doing. What I tell before, what I said before is that we took the spherical symmetric word metric, and we're working on the Einstein's equations. We're working on what's going on with some of the energy conditions, uh, and we're trying to see if which is the matter content that is the proper matter content that we can use this here, that is compatible and is consistent with the Einstein's equations that we found already. And one last thing that we want to do is that these equations, uh, when you have a spherical symmetry, this can give us some of these equations, some uh, equations that it looks like some set of equations that describes that are used to describe shockwaves, and we are trying to look what what is going on in our system if we try to look for these equations, which is these equations are very nice. These are connected with the fact that if you have some specific density, some specific pressures, and you have some differential equations, these all things, the whole thing looks very similar to some problems that are already known in fluid dynamics. So we use some of these similarities, and the same we're looking for in the spherical symmetric problem. These are called the Borcherds or Borger's equations, and we want to see what happens in this.
So, Nelson, that's really interesting. So, I just want to speak about this a little bit. So, we're currently finding some similarities between how space-time behaves and how the shockwave behaves. So we find certain similarities there, which is really interesting. And also, I know that in the past we observed different similarities between the Rayleigh-Pleasant equations, how they describe the bubbles, and how we describe the bubbles as a warp bubble. So there are a lot of similarities, and the Rayleigh-Pleasant equations they actually describe the behavior of the bubbles in the fluids. So it seems to me that space-time shows a lot of properties like a fluids because we see a lot of similarities like a bubble creation, the Rayleigh-Pleasant equations, or like the shockwaves equations with burgers. This is very interesting. I think there is something there. So we're going to continue working on that, trying to understand it.
Yeah, that's it's very true. Very true. This is something that is known. There are analog gravity approaches that uses fluids as the stuff that makes the space time. Of course, these are limited somehow to some. I'm going to dare to call it a phenomenological approach of the problem, because you have differential equations that are pretty similar to fluid equations, and maybe you can have a lot of information here, but in a sense, it's telling you something. Yeah, space-time follows some dynamics that looks a lot like some fluids, and there are some clues there in the direction of what is space-time itself. There are some words in that direction. And as you said, the Riley-Placid equations is a good example. Also, you have a cosmological model that you have the Freeman-Rosen-Walker problem, and it resembles pretty much an important part of the Riley-Placid equations. So yes, I agree. There is some work done in that direction, and I think one of the important things about working in warp drive is is that we are looking for something. Of course, we're looking to solve what we think is a very important problem, to see if it's working or if it's not working, and to look if it's not working, to look for any other options, and if it works, to see how can we use it. But the most important part, I think, is at least at the moment, is we need to understand, to approach these problems. You need to go deeper into what is space-time, how is it behaving. Uh, there are a lot of geometrical details here and there that are very important, then that question comes: what is space-time? Because Einstein give us he gave us Einstein's equations, which tell us exactly how space-time is going to behave, but it does not tell us anything about what is it space-time. So yes, this is very nice.
Awesome.
Well, at least this as far as I know.
Yeah. So Nelson, quite interesting and very exciting. So thank you very much for the overview. And we're going to keep pushing in this direction. And to all the listeners, if you like our work, if you want to support us, please like, share the video. And if you want to become supporter of our channels, you can do this on Patreon. Links below the video. And with that, thank you very much for listening. And I wish all of you to have a very nice and successful week.